Welcome back for the last video for chapter 7. I just really want to make sure you've got lots of practice with the normal curve and the central limit theorem for means and proportions. So example 11 says, the distribution of income in some third world countries is considered wedge-shaped. Many very poor people, very few middle income, and even fewer wealthy people. Suppose we pick a country with a wedge-shaped distribution. Wedge-shaped meaning skewed. So either something like that or something like that. Okay. Let the average salary be $2,000 per year with a standard deviation of 8,000. We randomly survey 1,000 residents in that country. So in words, X is the salary of a resident, and then X bar is the average salary of a sample. Okay, and so X bar is, we're going to say it's normally distributed, and we can say that because our sample is big enough. We have n equals to 1,000. So the average is 2,000. The standard deviation is 8,000 divided by the square root of the 1,000. D says, how is it possible for the standard deviation to be greater than the average? And that's because it's skewed. And so that's how we could always tell. Remember earlier in the semester, we said we can, when a data set is skewed, the standard deviation is going to be very high compared to the mean. Okay. So E says, why is it more likely that the average of the 1,000 residents will be from 2,000 to 2,100 than from 2,100 to 2,200? And that is because it is skewed to the right. The data is actually a skewed distribution. Okay, so we can find out both of those probabilities. So we said the average was 2,000, right? And we said, here's one sliver. What is that likelihood versus this sliver next to it? And if we go to Desmos, we can see this. So in Desmos, we can see this here. And from 2,000 to 2,100 income, it's 15.4% of the people, and only 13.7 or 13.2% of the people have an income between 2,100 and 2,200. So that's the differences. And I will label those on my graph here. Okay. So let's go back to the graph. So that one, and that is that one. So example 12 says, which of the following is not true about the distribution for averages? The mean, the median, and the mode are equal. Well, that's definitely not true. The area under the curve is 1. That is true. The curve never touches the x-axis. That is true. Gets close, but never touches. The curve is skewed to the right. So the distribution for averages are, the curve is skewed to the right. So not the distribution of the averages. The distribution of averages is always normal. Always normal. In the distribution of averages, our mean and our median, our mode should always be equal. So that one is true on A. Okay, let's look at example. I moved some things around. So number 13 says, the cost of unleaded gasoline in the Bay Area once followed an unknown distribution with a mean of $4.59 and a standard deviation of 10 cents. 16 gas stations from the Bay Area are randomly chosen. We are interested in the average cost of gasoline for the 16 gas stations. The distribution to use for the average cost of gasoline for the 16 gas stations is, so the distribution for the average should be $4.59 for the mean, and then we have to use our standard error, which is this one right here, the standard deviation divided by the square root of n. That's what it should be. And example 14, it says, Never Ready Batteries has engineered a newer, longer lasting AAA battery. The company claims this battery has an average lifespan of 17 hours with a standard deviation of 0.8 hours. Your statistics class questions this claim. As a class, you randomly select 30 batteries and find that the sample mean lifespan is 16.7 hours. If the process is working properly, what is the probability of getting a random sample of 30 batteries in which the sample mean lifetime is 16.7 hours or less? Is the company's claim reasonable? So let's just see. We're looking to see if this seems reasonable. What is this probability? So there's the average at 17, and then we're looking at 16.7. And ever-ready batteries. Okay, so less than 16.7, looks like it's a very small likelihood, 0.01999, so less than 2%. So it doesn't, it looks like the company's claim is they have an average lifespan of 17. So I would say their claim is reasonable. It's not very likely, but what's interesting here is because this is not very likely and it really did happen, we have a sample. So maybe the sample was not random. That could be an issue, but we thought we took a good sample. It could be the true population life of the battery is not 17, maybe lower, right? Because we really did take a sample of 30 and they had an average lifetime of 16.7 hours, and that likelihood is really only 2%. So when something that's very unlikely to happen actually happens, we have to start to question, like, how did that happen? Okay. Or maybe a fluke. That's a possibility. Okay. So the last little piece is building on our central limit theorem, but we're going to talk about that using proportions. So we're going to use similar entries in Desmos. It's just instead of having means in quantitative data, we have qualitative data. That's the difference. So p hat is going to be x out of n. So x is the number that satisfy our successes, and n is the sample size. And it's normally distributed with our p from our population, what we think is true about our true population proportion. And then this is our standard error that we're going to use, which it says for the normal distribution of proportions, the z-score formula is as follows. So we're going to use, this is our standard deviation, is the square root of p times q divided by n. This is our standard error of the population proportion. So just like with means, with population proportions, we have conditions. So our condition 1 is the same as before. It has to be a random sample. Number 2 is independence, just like with earlier in this lesson. Observations are independent of each other. If the sample is collected without replacement, then our population must be at least 20 times larger than the sample size. And our condition 3 is the one that's a little bit different. So this one we have to show every single time to prove that our distribution is normal. We have to show that this is true. N times p times 1 minus p, that product, that multiplication has to be bigger than 10. And once we've satisfied our 3 conditions, then we can say our shape, center, and spread. We can say our shape is normal. We can say our center should be at the population proportion, and then our spread should follow this square root of p times q divided by n. So our last example for this lesson is in 2014, a Pew Research survey asked 1,821 random 18 to 33-year-old Americans if they believed alcohol was more harmful to a person's health over marijuana, and 69% said yes. So let's write down some things that we know here, that n equals 1,821, and the p is 0.69. Verify that the conditions have been met. So the first one is random. And as long as they tell us that we did a random survey, then we can say yes. So they did. The second one is independence. And if you've asked somebody the question, you can't ask them again. So it's without replacement. So can we say that 1,821 is less than 5% of all Americans? Yes, we can definitely say that. So that should be good. And the third thing is n times p times 1 minus p has to be, greater than 10. So n is 1,821, p is 0.69, and then 1 minus 0.69 equals, and so we're going to find out what that equals. 1,821 times 0.69 times 0.31, and it comes out to be 389.51, and that's bigger than 10, so we're good. Says describe the sampling distribution. So our shape should be approximately normal. And our center should be the mean of the p hat. So we're following this right here, the mean of the p hat should be what we think is true about the proportion of the population, which we said was 0.69. And then our spread is the sigma of the p hat, which is the square root of p q divided by n. And so that's p is 0.69 and q is 1 minus 0.69 over 1,821. Let's make sure everybody knows how to find this in Desmos. And so that's 0.0108. But as you can see, we just in our coding in Desmos, we can just put it right here in this. So part C says, so suppose you conduct your own poll of 1,821 random adult Americans, and in our poll, we find that 67% of them believe that alcohol is more harmful to your health than marijuana. So for myself, I just want to find out what is the probability that less than 67% of people actually really believe this. And it comes out to be 0.032. So it's not very likely, but we actually had that happen because we took our own sample and that's what happened. So we took a sample, and here's the 0.69, and our sample right here at 0.67 came true. And what did we say it was 0.03? We said it's 0.032. Okay. So we have to decide, like, why do you think this might have happened? List 3 conclusions. So similar to what we just said, it could just be a fluke that happened, that we sampled 1,821 people and only 67% believe that alcohol was more harmful than marijuana. Or 2 is maybe our sample was not random. Maybe our sample was biased in some way. Or the third thing could be maybe 69% is not the true population proportion. Maybe it's actually something less than that, but we don't know. So these are kind of our typical 3 answers here of like, why might a weird thing happen? Okay, as we move along. So this wraps up chapter 7. So you'll see that all the videos say chapter 7.1, but there is an assignment for 7.3, and it's just how the book labels the problems. They are all, everything I do in these videos for chapter 7.1 should support your homework assignments for chapter 7. Let me know if you have any help or any questions. If you want help, I'm happy to do that. And catch me back for chapter 8.